Good afternoon and welcome to the meeting. I'm Sarah Gary, the Executive Officer of the British Society of Soil Science, and I'm delighted to welcome you all to our 8th Zoom into Soil webinar. Today's event has been supported by one of our regional groups, the South West Soils Discussion Group, which is chaired by Lynda Deeks, who will be presenting today, and Hannah Bowley, one of the regional group committee members, will be leading the Q&A session. Before I welcome our two speakers, I'd like to introduce the British Society of Soil Science as hosts of today's webinar. We're an established international membership organisation and charity committed to the study of soil in its widest aspects. We bring together those working within academia, and we have a growing membership amongst practitioners implementing soil science in industry and those with a keen interest in soils. This year, we'll be running 10 of our Zoom into Soil webinars, and the next one in the series will be on Wednesday, the 4th of August, and it will be on the topic Our Living Soil. It will be an opportunity to hear more about the art and science programme Our Living Soil, which links two major international conferences, COP26 and the World Congress of Soil Science, which we will be hosting in Glasgow. The webinar will be free to attend as usual, and further information will be distributed after today's event. Before we begin, just some basic housekeeping. As there are so many of you here today, all your microphones have been muted. We'll be taking questions at the end of both presentations, and my colleague Hannah will monitor these for us. Please could you submit any questions that you have by 12:50 to allow us to get through as many as we can. Although there is a raise your hand button, we won't be using this unless the presenter specifically asks you for a show of hands. Today's presentation has been awarded BASIS and NROSO points, and if you're registered with either body, please contact us directly after the event. Finally, please be aware that we are recording today's presentation and it will be available on our YouTube channel after the event. So I'd like to now start by introducing our first presenter, Dr Lynda Deeks. Lynda's interest in soil started while she was undertaking her undergraduate degree in physical geography at the University of Plymouth, and she went on to also do her doctorate in the same department. After a 6-year stint at the Scottish Crop Research Institute, now James Hutton, Lynda joined a satellite office of Cranfield University based at the former Soil Survey of England and Wales office and hosted by Northwick, now Rothamsted Research. Lynda's research interests focus on soil's physical properties, primarily soil structure and management effects on structure, including soil compaction, soil water movement, contaminant transfers, and soil erosion. She's been involved with a wide range of consultancy and research projects that are driving change in soil management through enhanced appreciation of the economic, environmental, and social benefits that soil affords. In November 2020, Lynda officially became chair of the South West Soils Discussion Group, and we're looking forward to a lively discussion on a range of soil topics. Over to you, Lynda.
Right, let's see if technology works. Sharing screen. And it'd be helpful if I could find where everything is.
That's okay, Lynda, we've got time.
So can you actually see my screen?
I can see your screen, so I can see your screen.
Let's try this another way.
So if you've got your PowerPoint there somewhere.
Found it. It was hiding under the everything. I just got to get rid of enough other things.
A team's call going on at the same time. Very popular lady. Yes, we can see your screen perfectly. I don't know if you want to make it bigger. Perfect. Thanks, Lynda.
Right. Oh, no. Trying to get rid of some of the windows. Right, can you see my screen without the other box that I can see?
Thanks, Lynda. I can see just your screen. That's perfect.
Great. Right, thank you for that. Technology, wonderful. So let's explore soil structure and in particular soil compaction. So what is compaction? For me, my definition as I see it is a decrease in soil volume. The decrease in soil volume caused by a pressure or force exerted on the soil as a result of a pressure. Now, within my definition of soil compaction, I include both densification and consolidation. Now, I know some others don't include those, so let's explore that a little bit more. By densification, I mean when particles begin to move together and expel air out of the system, and we result in a soil that has a greater proportion of particles and a smaller amount of space between those particles. In addition to densification, we have a process called consolidation. And consolidation is focused more on the solid and liquid phase within the soil system. Now, interestingly, water itself, as pressure is applied, actually resists that pressure and doesn't change volume. So in fact, in a soil that is fully flooded or all pore space is occupied by water, that pore space we can apply a pressure to, and the structure of that soil would not be affected. Now, this seems a little bit counterintuitive to what we're often told, in that we are told not to drive on soil when it's wet. So let's unpack that a little bit. Well, my definition here of the water being able to support the structure relies on it being within a confined space. And in reality, that won't be the case. It's often that the water will be in an unconfined system. And because of that, as we apply pressure, the water begins to squeeze out. It also begins to drain naturally by gravity. So consolidation is partly driven by this, but also consolidation not only is about pressure being applied, but suction. And the suction might come from water being removed by plants within the system as they extract it to be used, and also through evapotranspiration or evaporation from the soil surface. So all of these processes of water draining and suction within the system act to bring soil aggregates and particles within aggregates much closer together. So I think we can all agree that whether our definition of compaction includes both densification and consolidation, or considers consolidation separately, we can all agree that bulk density can be seen as a useful expression of perhaps compaction within soil. Let's explore bulk density a little bit. So we have two soil samples here, sample A and sample B. Our sample A is not compacted, whereas our sample B is compacted. But we are within the definition of volume within the same volume of soil. So we have a similar area and a height in both our sample A and our sample B. So thinking about bulk density, within that definition of dry weight over volume, the volume here is constant. So the only thing that might be changing is the weight of particles. Now, we already said by definition of compaction is that the particles are moving closer together. So we can see that in the images. The particles in image A are slightly more spread out than in image B. So we have more particles, therefore we have a higher weight of particles within a defined volume. And that helps us understand why our bulk density for A in our less compacted soil would be lower than our bulk density of our more compacted soil. So knowing that, can we use bulk density to express how compacted a soil is? I'm going to use some data here from Archer and Smith. they looked at 4 soil textures: a loamy sand, sandy loam, silty loam, and a clay loam. Now, I've just expressed where those 4 textures fit on the UK soil textural triangle here. Now, within the example I'm giving here, we're going to explore just one bulk density. So for each of these soil textures, at a density of 1.2 grams per centimetre cubed, we're going to look at the difference in air capacity and available water. Now, from their data, what they found was the air capacity of our loamy sand was much higher than our clay loam soil. For available water, the silty loam had a much higher available water than the available water in the loamy sand. So at the same bulk densities, different soil textures have different properties as expressed by air capacity and available water. So why is that? Well, it's to do with pore size distribution. If we think about soil in its simplest form, it consists of a solid phase and a space between that. And that space may be filled by either air or water. Now, usually when we look or consider pore size, we often use volumetric water to look at this, because we can not only look at total pore space as expressed by the total amount of water that a soil can hold, but we can also break it down into functional groups based on key suction criteria of fill capacity and permanent wilting point. So if we begin to look at the total porosity to start with, we have 3 textures here: a clay soil, clay loam, and a sandy soil. And of these 3 textural soils, the clay soil has the largest proportion of total porosity, as expressed by the blue side of this graph, whereas the sandy soil has a lower porosity. Now, this at first might not seem to make sense, because we usually assume that the sandy soil would drain faster, therefore we assume it has a larger porosity. However, to understand this better, we have to understand the function of each of these groups. So we have 3 functional groups that we can describe. At the larger pore space, which we define as macropores, so this is from saturation down to fill capacity, this is where drainage occurs. So water in this lower suction end is what we describe as drainage water. Now we can see from these 3 graphs that the sandy texture soil has a much higher proportion of drainage pore space, which helps to explain that while it doesn't have the largest total porosity, in the functional groups of drainage, it has the highest capacity to drain the soils. If we look at the other extreme, at the finer end, so poor water space below the permanent wilting point, which we define as unavailable water because it's below the suction at which plants can extract it, we define this as the micropore space. And it's the clay soils that have the higher percentage of micropore space. And this helps us to explain, one, why clay soils remain wetter for longer than any other soil texture, but it also helps to explain why clay soils are slightly more susceptible to compaction as well, because that water, which is held tightly within the soil space, acts as a lubricant and places these textures at higher risk of being compacted by a force. So let's just go back to some data, the data from Archer and Smith. There was another observation that they made when they set up their experiment. Their experiment was meant to be set up at across a defined range of bulk densities. And what they found is that they couldn't, for each of the soil textures, achieve each of the defined ranges. For example, in the loamy sand, the lowest bulk density that they could achieve was 1.04 grams per centimetre cubed. Whereas the clay loam soil, a much lower bulk density of 0.3 0.72 could be achieved. When they then applied compaction, i.e. to compact the soil as much as they could, bulk density of the sandy soil was again the highest at 1.82, and the clay loam was again the lowest at 1.35. Now, I have heard it said before that sandy soils don't compact. Well, this data clearly proves that they do compact. And in fact, if our definition of compaction is bulk density, arguably the sandy soils compact to a much higher level. Now, why might that be? Well, we explored in the last slide that there was more macropore space, more of this larger pore space. And this allows particles to move to within that space. So there's more capacity within a sandy soil for particles to move closer together. At the other extreme, our clay soils have finer particles that already are close together. So there's less space for additional particles to move into that space. And that explains why we can't compress or compact a clay soil to as high a bulk density as a sandy soil. Now, there's also differences, again, with air capacity and available water content. From an air capacity perspective, then our sandy loam at the lowest bulk density had the highest air capacity, followed quite quickly by our sandy loam. And then our clay loam and silty loam were much lower. Now, we can explain that, again, by the fact that the loamy sands have this larger macropore space. So the fact that it has a higher air capacity makes sense. If we look again at the other extreme, i.e. where we've compacted the soils to its maximum bulk density, again, the loamy sand has the highest air capacity. So again, that is linked to the occurrence of larger pore spaces. Although we've occupied more of that space by moving the particles closer together, there's still a lot more capacity within that larger pore space to be available. Whereas at the other extreme, where our clay soils had the least amount of larger pore space and a higher proportion of very small pore spaces, it's not unsurprising that we lose that air capacity. With respect to available water as well, at our lower compaction levels, silty loams are shown to have the higher available water, followed by loamy sand. And our sandy loam and clay loam have the lowest available water. As we compact that water, as we compact that soil, we can see that available water in our loamy sand and silty loam actually achieve a similar level of available water content by the end, i.e. at our extreme compaction that we can achieve for either ends for either of these soils. And the lowest available water is achieved in our sandy loam and clay loam. Now, this is quite an interesting fact to understand, because what it's saying here is that our loamy sands, potentially, which we see as droughty soils, could actually be improved in its available water content by applying some compaction. And in fact, the loamy sand soil here at our maximum compaction that they could achieve was still continuing to increase. Whereas for the other three textures here, the maximum available water content was actually achieved at lower bulk density levels. So, for example, the silty loam had a maximum available water content of 23.6 at a bulk density of 1.37. So if we were able to control amount of compaction on soil, potentially we could manipulate it to our benefit to increase available water content to plants under droughty conditions. The other thing I want to explore here is if compaction degrades soil structure. I quite often hear people talk about, oh, structure has been degraded, we've compacted it. Well, what do we mean? Structure consists of a range of definitions, from granular, blocky, peaty through to massive. At the granular end, we can describe this as being less stable, and as we move towards the massive end, structure becomes more stable. So are we degrading soil by compaction because we're moving it from less stable to more stable? Well, if our perspective is from an agricultural angle, then perhaps we are. So for agriculture, we favour more granular soil, although as we've seen from the previous slide, if we compact it slightly more, we might get benefit from improving available water content. But if we compact it too much, then we know yield begins to decrease. However, if our perspective is more from the construction side, then our desirable soil structure would be towards the more massive structural component, which is more stable. And our least desirable would be granular because of the fear of subsidence. So I would argue that soil structure itself isn't degraded by compaction. It is changed by compaction, but it's actually the function that is changed. But whether the function has degraded very much depends on your perspective on what you want to use the soil for. The other aspect of soil compaction is its influence on infiltration and runoff. So in a healthy soil profile, we would expect with depth the soil to become slightly less permeable as we go down because of the overburden of the soil above compacting the soil layer below. But generally in a healthy soil, we have an expectation that water that's applied to the surface will infiltrate and then percolate down to depth. And the soil each soil has a capacity to absorb this water at a known rate. However, we also know that management can create compacted zones. We can have zones of subsoil compaction, and we can also have zones that are at depth within the soil profile. So these compacted zones at depth may be the result of us undertaking a particular process, such as running a plough through the soil at a consistent depth for a repeated operation. But they can also be caused by, in the construction industry, where soil is removed during the construction process and the layer below is trafficked with vehicles during the construction phase before the topsoil is replaced. So what are the effects of having this subsurface compaction zone? Well, firstly, it can inhibit the amount of water that actually goes through the soil to depth, so effectively limiting the actual capacity of the soil to store water. And the higher up this compacted layer is, the less capacity the soil has to store water before it reaches its potential runoff. So if we have a compacted layer right on the soil surface, and this might be the result of us trafficking, walking or driving across it, or it can be as simple as a raindrop or irrigation drop falling on a fine-till soil, causing compaction, we can develop what we know as a seal or a cap. And this seal or cap can be just a few millimeters thick, as shown in this figure here. But the effects of that are to reduce infiltration, limit the capacity of the soil at an even higher level, and promote overland flow, resulting in an image like we see on the left here. So hardly any of the water has infiltrated into the soil profile, and most of it is running off that parcel of land out through the gate and potentially increasing the risk of downflow flooding. But is it all bad news? Well, a bit like our water, which resisted the forces protecting the soil structure, a compacted layer at depth can offer protection to the soil structure below. And even at the surface, it very much depends on whether a seal or a crust is being formed. So a crust is where the actual surface has formed cement. Minerals within the soil on drying have cemented the soil particles together, forming a tough surface through which it's hard for vegetation to penetrate. However, if only a seal is formed, so we don't have that cementing, then actually from an agronomic point of view, we can use that to our advantage. It can actually serve to maintain moisture and promote more productive growth of seedlings by allowing an environment in which they maintain a moisture content that promotes growth. And providing that seal isn't too hard, then seedlings can easily burst through. Now, I haven't got a lot of time, but I think it's important that we do consider how we might remediate compaction. And I'm simply going to look at two options here, the mechanical option and bioengineering options. So the mechanical option, and by that I mean using plough or subsoiler, is our more traditional approach to remediating soil compaction. Certainly it's a quick solution, and when done at appropriate times seems to be very successful and is well liked by most people. I've put fine tilth here, but what I really mean is that mechanically we can produce a tilth, so a soil aggregate structure that meets our specific requirements, be that a fine tilth for fine contact with seeds or a more rough tilth to prevent soil erosion. However, there's also some negative sides to mechanical alleviation of compaction. Although it breaks up the soil, it leaves it in an unstable and vulnerable state to compaction. If we liken it to a building being built out of bricks, but forgetting to add the cement, then that's similar to what I mean by the mechanical breakup of soil here. We've created the structure, but we haven't given it its resilience because we haven't given it any support. If we do it at inappropriate times, i.e. when the soil's wet, then the actual process itself can lead to further compaction. It's also limited in the depth range over which it can be used, by the depth we can pull the plough through, both from a power perspective and economically. And it's also very disruptive to habitat. So an alternative might be bioengineering, and by this I simply mean here cover crops, although there's other options. So bioengineering can form a more stable, more resilient structure because it forms structures by penetrating roots through the soil structure, flaking off cells from the root system, which acts as cement, forming a stable structure. The advantage of using root systems is that they can extend over much deeper depths, so in excess of 2 meters has been recorded. They definitely provide better connectivity from the surface through to depth of the soil profile. And they also help support soil habitats by their nature. But there are disadvantages. Certainly they take a much longer time to develop, and there's been variable reports of success from different operators. And there's also potential for competition with other vegetation, so competition by access to water and nutrients. So just to conclude, is compaction good or bad? Well, certainly it changes pore space, and also it does change soil structure. However, while this might impact soil function, it has both positive and negative implications. And the take-home message here is that it very much depends on your perspective on the problem. So I hope you enjoyed that, and thank you for your attention.
Thank you so much, Lynda. That was super and really interesting presentation, particularly about perspective and what you are looking at the soil function in regard to, whether that's agriculture or construction, for example. Really interesting. We'll be taking questions for Lynda after we have had Bruce's presentation. So I would now like to introduce Dr. Bruce Lascelles. Bruce is UK Director for Land Management and the current President of the British Society of Soil Science. His background is in soil science with a degree in forestry and soil science from the University of Wales in Bangor, and he has a PhD in from the same university studying the environmental history of an upland area of North Wales, bringing together an assessment of vegetation and climatic change, soil development and human influences on the environment. Following this, Bruce undertook various research on various aspects of soils, particularly soil erosion, before becoming a consultant, where for the last 24 years, he's worked on aspects of the interrelationships between the physical environment and plant and animal communities. A key area of his expertise is in soil and hydrological assessments and the development of strategies for the creation, restoration and translocation of valuable habitats. This has included work on a wide range of habitats, including lowland raised bogs, blanket bog, wet and dry heathland, marshy and chalk grassland and woodlands. Bruce has also been involved in a wide range of major infrastructure projects, assessing soil characteristics and land quality and developing soil handling strategies. So without further ado, over to you, Bruce.
Thanks very much, Sarah, and thanks, Lynda. Yeah, it was an excellent presentation, and I'll definitely touch on some of the points you raised. Is compaction good or bad, and that point around perspective. Can everyone see my screen? See the presentation?
Yes, we can. Yeah. Thanks, Bruce.
Brilliant. Fantastic. Okay, so what I want to do is perhaps pick up on some of the points that Lynda raised around soil structure, soil compaction, but very much from a construction perspective. And so I guess first of all, construction sites, these will range in scale from perhaps a small house extension to major schemes such as housing developments, road schemes, and projects like HS2. But all of them are likely to involve heavy plant of the sort you can see in the pictures on the screen from some major infrastructure projects. And the size of these machines, and in particular the extent they work across the ground surface, can result in, and probably does result in soil compaction. They can have very high ground pressures, and I know there are good examples now of low ground pressure machinery where the ground pressures, even on a big machine, can be as low as perhaps 5 pounds per square inch. But it's perhaps more about the number of passes the machines make. Does the machine skew, so where the tracks rotate in different directions so the machine can change direction, because that can scuff and smear the ground and result in additional soil compaction. And the type of machinery that's being used, where it's being used, how it's going to handle soils, etc. Those are all really important things to think about when designing a methodology for soil handling, and particularly what plant to use, and in particular what sort of restrictions you want to put on how that plant operates and where they operate. But before I talk a bit more about sort of soil compaction and construction sites, it's important to recognise, and this perhaps comes back to one of Lynda's slides, that not all soils will end up being used for the creation of perhaps soil profiles to support agriculture or habitats or landscape planting and so on. And some materials that we might think of as soils, or we do think of as soils, may be deemed suitable for use as fill materials. And those fill materials will probably have an engineering requirement and need to be geotechnically stable, and thus they'll need to be compacted. So that Lynda's slide there, where showing the housing development and agriculture at two ends of the continuum. And so, you know, we need to be conscious, and it comes back to that point about perspective. We may not wish to see soil materials compacted, and we may write that they shouldn't be, but actually that can be an essential part of what happens on construction sites to produce, for example, the final landforms on which landscape planting areas will be created, or platforms for the building of structures of houses, etc. And I've just put on the screen there just part of a table from a document known as Series 600, which is part of a series of highway specification documents, but it's widely used on many construction sites to define the characteristics and uses of excavated materials. And it's a very large document, so I've just pulled out a couple of clips from it to give you a sense of where materials we would define as soils could end up in an end use where they're requiring a certain level of compaction. So we've got descriptions here of wet cohesive material, dry cohesive materials. That could be subsoil material, and in particular then we've got materials which are classed as class 4 and class 5. So landscape fill, very often this will be subsoil material, and then we've got a sort of a classification for our topsoils and turf, etc. And I suppose the point of putting this on in the presentation is that a key part of perhaps designing a soil handling strategy on a construction project is to maximize the reuse of the materials and to really minimize the export of a surplus or the need to import materials. So really sort of driving from a sustainability perspective. So ensuring that surplus soil materials are used in the design, even if it means that they're being compacted to a level which you know we think is absolutely totally wrong for soils, may be an absolute critical part of the project. The other point I wanted to raise was also that it's important to note that construction sites are not simply where soils are stripped to make way for the construction of a hard engineering structure such as a road or railway or housing. And across construction sites, there'll be many very different elements to design, which may include landscape planting, SUDS or sustainable drainage systems, habitat areas, grasslands, playing fields, allotments, and those sorts of things. Even cemeteries as well. And this is a master plan from a housing development on the edge of Bicester that we've worked on. And you can see some of those elements there, and I can't remember the exact numbers for Bicesters, but very often some of these large housing schemes can have up to 50% green infrastructure. So 50% of the site is not a house or a school or a community area or shops, etc. And while some of those features may need to be recreated once the site's been stripped, because obviously the activity will move around the site. On a project like this and thinking about construction activities and soil compaction, clearly there's a real need and desire to seek opportunities to not disturb the soils in these sorts of areas, so that we avoid that risk of soil compaction and the risk that the soil function won't be suitable for the desired end use. And particularly where we've got large areas here, so the slight sort of yellow colouring, these are particularly habitat focused areas. Clearly, not going in and tracking of the soils and causing compaction there is a really positive step to generating the habitats and the green open space that's needed as part of the design. And this is another example where works on a major construction scheme. So this is a road project in North Wales. We're focused specifically on habitat translocation. In this case, the translocation of some valuable floodplain grassland. And on this project, we came up with a very detailed design for how soils would be lifted, what machinery would be used, where they'd be placed, and so on. And a specialist contractor was brought in to deliver those works. And the soil handling here was done by low ground pressure machines. So we've got dump trucks with rubber tracks on them. We've got wide tracks on the excavators and so on. And also, again, to minimize the risk of soil compaction, and on the basis of the nature of the habitats and how valuable they're perceived to be, these soils weren't scraped up and stripped. So we're trying to minimize the impact on the soils. And in this case, then this was done by macro turfing. So this is taking cutting a turf, and these are about 1 meter by 2 meter in dimensions, cut to the base of the rooting zone. So we're holding all that soil together, and those are moved to really reduce the risk of soil compaction. But actually, when we think about soil compaction, it's worth noting that on this site, and this comes back to perhaps some of the earlier points, is soil compaction good or bad? We would normally make a very clear statement that on a site like this, placed soil should not be tracked over. Once they're placed, and no more machinery should track over them. But when we're looking at macro turfing in this situation, these turfs, once they were placed, were actually tracked over, but in a very careful and a very managed way. But just to make sure that the turfs had bedded in properly, we didn't have air pockets under the turfs, and they really sort of butted up against each other really well, so there weren't any gaps. So again, that balance and that perspective that we don't want compaction, but actually there's a level of compaction that soils naturally have, and we have to try to get back to that as well. And I think I've got one more example. This is an example of a site, another road scheme, sorry, in South Wales, where part of the project design was the translocation and the reuse of hedge materials that were in the way of the new scheme, but were being reused to create new hedgerows. And you can see here where the excavator that's placing the copper stools in the trench has been tracking back and forth, and you can see here where it's skewed a little bit, and it's been sort of starting to tear and smear the ground. So the ground there will have suffered compaction, but as that area was going to remain as grassland as part of a biodiversity mitigation strategy, and the site had only been accessed during dry weather, in all probability, the natural processes that Lynda talked about will alleviate that compaction. So actually trying to go back in and say, we've compacted the soil, we need to deal with that, potentially has the risk of causing more problems. And I'll show you some of those sort of problems that can happen later on as well. So just checking all the time. Yeah, so there is, oh, sorry. Sorry, I've got a very sensitive mouse. Why is it not going back? Bear with me. You're getting a preview of what's coming up. Right, back on track. Okay, here we go. So there is guidance to support decisions around soil handling approaches, and essentially they're designed to minimize the risk that the soils are not in a state and won't function as required for the end use. And in particular, there's the Construction Code of Practice for sustainable use of soils on construction sites. There's also a suite of MAF good practice guides for handling soils, and notes such as the one that the British Society of Soil Science have recently published on soil management in development and construction. And there are other documents available as well. And these are really valuable documents. In the absence of primary legislation relating to soils, we need published guidance to refer to, and we also need to strengthen our collective voice around these. And a good example is a few years ago, I was working on a project in Wales, and I'd included reference to the DEFRA code in my proposed mitigation, and a review comment came back from the client team asking me to delete that reference because it was a DEFRA document and therefore was only relevant to England and not relevant in Wales. So we do need to start really increasing our voice around the need for these guidance documents to be followed. And if that guidance is followed, soil handling can be done well, and post-construction issues around soil compaction can be avoided. But as you'd expect, problems do happen and things do go wrong. And this grainy picture here is not a result of my poor photography skills, but it's an image taken during torrential rainfall at a site in Wales a few years ago. And you can just about tell that the workers are ankle deep or deeper in silt-laden runoff, which is coming off the working width for a pipeline installation project. And a number of things went wrong that day, not least that works were not stopped when the site made secure in advance of the rainfall. And unfortunately, one of the results from this was that some of this silt made its way into a reservoir, with all the consequent financial and reputational damage that comes with that. But also there was soil compaction because works continue, soil handling operations continue during some of that weather. And this is the sort of thing we get left with. You can see here, this is another road scheme in Kent, where ancient woodland material, so soils and stool materials, were to be salvaged through the following of a very detailed method statement that we'd written. However, the vegetation clearance activities which took place in advance of the soil stripping were not controlled in line with that soil handling strategy, meaning that those works continued during poor weather conditions, leaving significant areas rutted with topsoil and subsoil mixed and water ponding as a result of the compaction. And these soils were going to be stripped, so essentially we had the opportunity to remove the compaction through the process. But a key problem here is that these soils supported highly sensitive habitats and were very, very thin, and the strategy involved the salvage and respreading of the surface litter layer, which clearly in some areas of the site following the vegetation clearance was not going to be possible, and so some of the soil handling strategy had to be adapted as a result of that. And when looking at when, or perhaps when soils should be handled, but also that it's important about the resilience of soils to that handling. And I've just pulled out this from HS2 document, which is their technical standard for soil handling. And as perhaps I hope you picked up from Lynda's presentation, really it's that the texture of the soil is really, really important, but also the amount of rainfall and that water holding capacity of the soil is important. So this table essentially defines much of the soil handling strategy on HS2 in terms of how soils were handled and also identifying their risk of structural damage due to handling. And you can see here, for example, we've got the light texture soils in low rainfall areas have a high resilience to structural damage, whereas either our medium texture soils in high rainfall areas or heavy texture soils have a low resilience to structural damage. And again, I should say, coming back to perhaps some of Lynda's points, this is really focused on the reuse of these materials for agricultural purposes. So the soil, the integrity of the structure of the soil and its presence in the soil is really, really important for the successful reinstatement of those soils. So to just look at a couple of examples. This is a site where an area of woodland needed to be created, quite an extensive area would need to be created as part of a guided busway scheme, as part of mitigation for that scheme. And the area is colliery spoil. There have been past phases of land restoration here, which haven't been hugely successful. So there's very little soil to work with, but we did have soil forming materials from the main construction works and access to locally sourced PAS 100 compost. The real challenge here was to create a soil profile that wasn't compact at scale against a tight program and moving into a difficult time of year. So the works were planned to start early autumn. They probably didn't really get going until early October, I think at the earliest. And on many projects I've worked on, we've been very lucky with weather in that sort of autumn window with significant dry periods to allow works to progress rapidly. But in this instance, the forecast wasn't looking so kind. So we had to come up with a methodology which would allow the very rapid progression of soil placement. And this involved the initial windrowing of the soil materials and the soil forming materials, starting then to sequentially spread these in the defined and required layers across the site. And actually what we allowed in this case was the creation of putting the subsoil in, the creation of a compact surface to allow the machines to continue to work over, and in particular to allow bulldozers to work, which allow the works to progress as fast as possible. But ensuring then that before the next layer is put on, there's some decompaction, and then there's full decompaction of the profile, as you can see here, through deep ripping prior to the spreading of the compost. And then we start to move to just standard agricultural machinery, so much lower ground pressure, fewer passes, and ending up with a very good cultivated surface. And this process was really, really successful in creating a soil profile with good structural units and fissures. And I should say that's a good soil profile at that point in time. Clearly, then we need those natural processes to maintain that soil structure, but also to make that soil structure more resilient and stronger as well, so it doesn't just degrade over time. But nothing as it ever goes to plan. So this is another example of a major construction site where the soils had been started to be placed without supervision. And actually what had happened was topsoil had been placed immediately onto the overburden, and then because it was a sloping area, had been just run back and forth with a bulldozer to really compact it. And actually it was pretty difficult to dig by hand, and we were left with it was a heavy soil anyway, but a very compact material. So the solution here was that the topsoil had to be removed, and then the full process undertaken to place and loosen subsoil over the overburden in a sequential way. And you can see the way the site team was starting to work the way out of the site. And on this site, absolutely no tracking over the final prepared surface, and then the use of agricultural machinery to do that final cultivation. And after the first winter, going back in the spring following, the structure that had been created was still present. It was still a loose soil, easy to dig, despite the heavy nature. And actually the vegetation that was starting to establish, you could see visibly that the roots were starting to bind structural units together, and it was starting to get some of that strength it required. So actually, you know, despite a not so great start, a really good end result to that project. But I mentioned earlier about sort of soil compaction and whether we do go back in and deal with it. A key point of these sorts of programs is that a huge amount of money is invested in the right techniques, the right plant, the right personnel to ensure the works are done correctly, and that can very quickly be sort of thrown out the window if the post-construction activities are not regulated to also avoid compaction. And so on this site, again, successful placement of soils and the structure, the trees were establishing, the grass was growing, but then post-construction activities resulted in quite some significant soil compaction, you know, rutting, displacement of soil. So this is just the soil that's been displaced from a track that's been used into a large mound. And the compact soils visibly being waterlogged, holding surface water, and so on. So we produced a number of reports on there, and definitely for these two sort of major trackways, they'll be repaired. But for these two locations where the damage has happened between the planted trees, we did pose the question: should we go back in and remediate that? And actually, in this case, the recommendation was that we wouldn't. To go back in, you've got to get the contractor back in. There's a risk of more damage happening, works happening again during poor weather. And actually, as this site matures, it's a landscape area, so as it matures and as the natural processes really start to kick in, that compaction will be alleviated, and possibly that will add, you know, at least in the early stages of the development of the site, so some additional diversity to the ecology of this location. I'm very conscious of time, but I will just quickly just show you this this example. Again, construction related, but not a result of the activity of plant or soil handling activity. So this is a location where we were working on a scheme for the development of underground storage caverns for natural gas. But within the site, there were existing disused saline solution mines, which had all been capped. And one of those failed, and you can see that here, and it spewed out a significant volume of sort of hypersaline liquid mud across a number of fields and roads, which very quickly and very significantly affected vegetation, so hedgerows, grass, trees, etc. But we were also asked to look at the longer term impacts of this on the soils, and one of the effects of that saline sort of intrusion into the soils is the breakdown of structural units. And it's perhaps not too easy to see from this side, but this is a sod from an unaffected part of the field, and this is a sod from an affected part of the field. And actually, the analysis was that there was already quite a significant sort of change in the density of the soil, and as a result of that, just natural breakdown because of the sodium input into that soil. And those soils now will be much more vulnerable to further structural damage on handling or cultivation, which had to be taken into account in planning the remediation of that as a site. So yeah, thank you. I'll leave it there. I'll just leave you with one just reminder of the World Congress of Soil Science, which has been mentioned already. It's coming up. Planning is going really well for it, and we'll soon be opening up calls for abstracts and registration. And we will need a pool of volunteers. So if you're interested, do keep in touch and watch our website and email alerts for announcements and calls for help on that.
Thanks very much.
Thank you.
Thanks, Bruce. That was really interesting, particularly the solutions you went through and how to minimise the impact. Hannah has been monitoring the questions you've been sending in, and she will ask your questions of the panellists. I know we have a few waiting to go. So over to you, Hannah.
Thank you. Yeah, so for Lynda, there are a couple which I hope I can sort of put together. One question was, how do we mitigate animal impact, whether that's grazing or trampling, on compaction in the UK, where the soil remains wet for the most part of the year? And also a question about which crops could be used to alleviate deeper compaction and how long that might that take. I put those together because I wonder if one might be the answer to the other.
So,
but if they're not, then
wetter ground. We certainly have a lot of that down in the southwest, and it's possibly not going to be the most popular answer. But what we definitely did find with a little bit of research that we did down in the Boscastle area, that we know that if you reduce the intensity of the farming, i.e. reduce the number of animals on that field, that you very much do protect the soil. You get far less poaching of the soil surface. The grass is also in a better condition. I guess why I hesitate slightly, we were also looking at whether the grass had been in permanent lay or lay grass, so over 5 years or under 5 years. So definitely the combination of having a permanent grass cover that's helped, has been there and has developed a sounder soil structure. So you've still got the sort of the matting below the grass itself, that protected the soil underneath it. So one, minimizing the amount of animals. The New Zealand system also seems to work well, so applying that pressure for less amount of time, and so you might cordon off areas of a field and only allow the animals to graze for a day or two before moving them on to the next parcel. Providing you have sufficient amount of land to not have to return to that first parcel for a good few weeks, then that can actually work well. As to which plants you use, it very much depends on the situation, i.e. the cover crop has to be compatible if you're going to use it in an agricultural system to be acceptable within the rotation. Sometimes it can be complementary, i.e. offer additional benefits through chemical suppression of the likes of nematodes and other biological benefits through fungal associations as well. I'm desperately trying to remember the name of the taproot. It's definitely a grass, and it'll come to me at some point, but certainly it's not necessarily about the length. Hannah, was a question specifically about the deepest roots?
The question was from Layla Froud, who may be familiar to you, about alleviating deeper compaction. So I don't know if you want to talk to her later about it or get in touch perhaps.
Yeah, certainly there are different species, and it depends what fits into the actual program, or what you're using that parcel of land for, and it depends what country you're in. So the one I'm desperately trying to remember, and it will come to me eventually, but they started using it in the Netherlands, but it was so prolific, the root system, that they actually had to stop using it because it got into the drainage system.
Not Lucerne?
Lucerne, thank you. Yes, Lucerne. Yeah, so that is one of the deeper rooting plants that has shown some benefit to alleviating compaction at depth. So
we have also got a variety of slightly more technical questions. I can see that there is 1 minute left until 1 o'clock, so I'm going to say to Bruce, I wonder what how these the construction companies, how keen they are on actually taking care of the soil, and you're talking about taking off layers of turf or what have you. Does all that tend to happen under duress, or is there some kind of awareness among construction companies that this actually is an important thing to be doing?
There is, and it's important to recognise that many of the requirements of what happens on a construction site are driven through the planning process. So whether it's a local planning authority or the planning inspectorate if it's a major infrastructure project. And so yeah, so macro turfing is a great technique for minimising the disturbance to the soil, but it comes at a price in terms of time, how long it takes, and cost in terms of taking longer, but also the machinery, etc., and bringing in specialists. So we do need to be measured with how that's used, but it is a technique that can be used very, very successfully. But that will probably be driven through the planning process as a commitment and requirement from the planning application or the development consent order. But I definitely over my career, the recognition of soils as a material that's not just shifted, and there's this phrase muck shift. Soil is not muck, but if you talk to a lot of contractors, they'll say, oh, it's a muck shift operation. We just get a big digger in and a big haul truck and move it. But we're definitely moving away from that, and I think particularly, and hopefully later this year we'll have a very sort of focused HS2 discussion in one of these sessions. The recognition and perhaps some of the scale of the projects that are going on at the moment is really drawing everyone's eyes to it, and absolutely contractors have to get it right and are trying to, and really the will is there, definitely.
Well, that's good to hear. There are lots of other questions, but I've seen Sarah has appeared, so
yeah, I don't think we're going to get to those. Thank you so much to our speakers, and we will take those questions away, and where possible we will try to answer them after the session. I'd just like to express my thanks to both Lynda and to Bruce for coming along to present today, and to, of course, Hannah for taking questions here at the end. And thank you all for attending. Though you will find a quick feedback survey at the very end when you leave this webinar, which we hope you will take the time to complete. As I said at the beginning, a recording of this video will also be available on our YouTube channel from tomorrow. Our next Zoom into Soil session will take place on Wednesday, the 4th of August, as I said earlier, and there won't be a Zoom webinar in September, as we'll be hosting our annual conference and AGM on Tuesday, the 7th of September. The annual conference theme is soil health, and the half-day session will include a number of invited speakers and panelists on the topic. The conference is completely free of charge for members of the Society, and if you're a non-member and the event sounds interesting, you can become a member via our website for £31 and access that conference for free. I hope to see you all at future events, and in the meantime, thank you once again and goodbye.